Welcome to the last video on the convergence of series, and in this one we start off with the ratio test. And the ratio test, and I feel you might want to kill me after I tell you this, is probably so useful, so standard, that you pretty much forget about the other ones. But sometimes the ratio test is not enough and you will need the other ones here and there occasionally. But let's be frank, most of the time you'll just use the ratio test. So how does it work? If we have a series, here's my series. Let's call this series A from 1 to infinity. Great. When the limit of a term and the previous one, or a term of the next one, okay, a term divided by the previous one, the absolute value of that, as it goes to infinity is smaller than 1, the series converges absolutely. When the limit of ak plus 1 divided by ak, the absolute value of that gives me 1. We don't know. The ratio test is inconclusive. We'll have to look for different ways to solve it. And when it gives me bigger than 1, the series diverges. It's very powerful. You will be able to use it most of the time. This is the ratio test. There you go. The last I've been keeping this one for last, and you will pretty much be able to solve most cases with this one. But sometimes it will involve a lot of work, a lot of algebra, so the other ones might be quicker too. However, very important, when k is a power, this will be very useful. When I mean like 2 to the power of k, 5 to the power of k, and you can't just show that it's a geometric series, this will be very useful. And also if you have factorials, and you will end up with a lot of factorials, trust me. So that's it. That's the ratio test. Very useful, the most useful tool. There you go, you got it. So let's use it. Let's go ahead and use it. Let's use it first in a difficult one. So here you go. Converges or diverges? Take a look at it. K factorial divided by k to the power of k in alternate series. Interesting. Okay, let's use the ratio test. So here's my ratio test. Absolute value of this thing here. Okay, the -1 and the 1 here becomes minus, but that's absolute value, so that can go away. Okay, here you go. Let's multiply this times the 1 at the very bottom. I end up with this expression here. Well, k plus 1 factorial is k plus 1 times k factorial, right? So let's write then k plus 1, all of it times to the power of k plus 1, is k plus 1 times k plus 1 to the power of k. So I can end up with this expression here. And I can cancel quite a few of these things out, right? When I cancel quite a few of these things out, I end up with limit as k goes to infinity of this thing here. But this thing here is just this thing here. And here's an important thing. This is why this one is not that easy. Because it might be tempting to say, well, you know, k is to the power of k on the top here, right? And in the bottom I have k to the power of k, and then something with something k to the power of k minus 1, and then, but you know it's to the power of k minus 1, so maybe it's 1, because I end up with k to the power of k in both numerator and denominator. No, you can't do that. Why? Because I can do it if I have k to the power of 2. That's great. But not if I have an infinite power. You know, I have an infinite number of elements here. So what can we do then? Well, okay, so I have this thing here. Let's rewrite it. Didn't you agree that it's the same thing as this thing here? Okay, just turn it around. So, you know, you have this times this divided by this. Great. This is the same thing as this thing. Now let's look at the denominator here. I can rewrite this in the following way. Do you agree? And we should talk about the step I'm about to make here, but I can say, well, this thing's the same thing as this. Huh. Okay. Now, have you seen this before? Have you seen this before? You will be expected to know this, and I'm sure a lot of you are thinking like, but why? This thing here gives me 1 divided by e. Why? Because you should know that the limit when n goes to infinity of 1 plus 1 over n, all of it to the power of n, is e. That's the definition of the number e. So here, when I end up with this expression here in my limit, the result is 1 over e. And that's smaller than 1. So by the ratio test, the series converge absolutely. Great. See how the ratio test itself is not that hard. The thing is that I wanted to introduce this use of e here. Let's do perhaps an easier example. This one here, again with factorials. So we'll use the ratio test again. Again, I do the next term, so k plus 1 factorial divided by the square root of k plus 1 factorial. Absolute value of the whole things. Now the absolute value, don't really need it. I can get rid of it and let's just multiply. And again, I do the same thing with the factorial here. I end up with k plus 1 times k factorial. And here I do the same thing with the factorial. Now this, because it's a square root and it's multiplication within the square root, I can separate it. And now I can cancel some of the things out. When I cancel these things out, I'm going to end up with this limit here. And this limit here is going to be bigger than 1, because the power in the numerator is higher than the power in the denominator, right? So quite simply, these series are divergent. And that's it. And that concludes our examples. Now we are going to do a lot of exercises, obviously, but let me close up this whole section on the convergence of series. So these are all the convergence tests we have studied. Tools. These are tools that you will use to analyze series, and you will be expected to know them. The geometric series, the quick divergent test, just make that limit, see whether it goes to 0. Comparison test, find one that's always bigger or always smaller. The limit comparison test, when you just can't use a comparison test. The integral test also allows me to put bounds. The ratio test, we just saw that one. And the alternating series test, which is just when the sign is going to be changing from minus to plus, and it has this little tricks here and there. That's it. Those are your tests. Those are your tools. So what with them? What are we going to do with them? We're going to use series to approximate functions. Okay, we're going to go back to analyzing functions like e to the power of x, etc. But this time we're going to be using series to analyze them. These type of series are power series, but within power series, we're going to be focusing more on a type of power series, which are Maclaurin series and Taylor series. So a very important tool of calculus. I look forward to it. See you next time. Goodbye.